Woo! Hello. Hello, everyone. Welcome to Engineering Thermodynamics. What we're going to be looking at is polytropic work. And what that is any process where the following equation is true. Where at the start of a process, we have the product of pressure and volume raised to some n index, and whatever that equals is at some constant such that it also equals the pressure and volume multiplied together at the end of our process, where volume is still raised to some n index. Now, if we just look at some classical examples where n equals 0, well, plugging that into our polytropic equation, that gets us volume that gets us volume dropping out, and we have P1 equaling P2. Well, that's true for isobaric processes. And therefore, our work equation, we can simplify it to work equaling pressure times the change in volume for any isobaric process. Now, if n equals 1, well, that just makes our polytropic equation become P1V1 equals P2V2. And, well, that's true for isothermal processes. And our work equation for that scenario will be the product of pressure and volume, either at the start or at the end of our process, multiplied by the natural log of volume 2 over volume 1. Now, usually we use P1V1 instead of P2V2 because it's usually easier to know the starting conditions than to know both the pressure and volume of the final conditions. If n is some substantially large number, usually it's said it's referred to it is at infinity. That means that the volume component of our polytropic equation is substantially outweighs pressure, such that pressure eventually drops out. This is similar to saying that V1 equals V2, or it's an isochoric process. And under that scenario, there is no work. Work equals 0. If n equals some other value that's not 0, 1, or infinity, such as 1.1 or 2.5, 0.5, whatever, we can use that's just a general polytropic process. And under that scenario, we can just use our general equation, which is work equals the change in the product of pressure and volume minus 1 minus the n index. To expand that equation, that gets us work equaling P2V2 minus P1V1 over 1 minus n. This is true for any polytropic process. It's just for the others, work was able to break down into a cleaner equation, one not as long. Now, there is a special type of general polytrope that is an isentropic process. Really, the only difference is in our work equation, instead of writing 1 minus n, we'll use 1 minus gamma. Gamma is the adiabatic index, and it's unique. It's a unique value. It's when the n index of a polytropic process equals the heat capacity ratio of a particular gas. This value will change if we're talking about air or carbon dioxide or oxygen specifically. The heat capacity ratio is just the heat capacity under constant pressure divided by the heat capacity value under constant volume. And this is true for isentropic processes. That is where a process occurs under constant entropy. And if a process from start to finish involves constant entropy, that means that it is a it is a reversible process. So if in your problems you hear about isentropic or you hear adiabatic reversible adiabatic process, basically we can just use our general isentropic work equation, but instead of 1 minus n, just know that n equals gamma in this scenario. Now, some other things that we can hear about, there's work and there's work rate. Work rate, you might see this symbol in your textbook. W with a dot above it, that means work rate. Work rate is just work divided by time. In other words, that's just power. Now, what we're going to be doing is a few examples from Thermodynamics Concepts and Applications, Chapter 4. This comes from the Cambridge University Press publisher, and we'll be using this for engineering thermodynamics sophomore level. 4.1 from chapter 4, air with a adiabatic index or gamma equaling 1.4 expands at a constant pressure of 200 kilopascals from a volume of 0.1 to 0.4 cubic meters. What is the work done by the air? Well, what really matters is we don't need an n index. In this case, we don't need that gamma value. Since we know that we're at constant pressure, we can just use our work equation, pressure equals, or work equals pressure times our change in volume. Plugging in our values, that gets us work equaling 60 kilopascals by meters cubed, and kilopascals times cubic meters is just a kilojoule. A little note on conventions. Now, usually when something can be positive or negative, we've usually thought of those as vectors back in physics. Well, work, that is energy. Energy is not a vector. It does not have a direction in physical space. However, here's the physical meaning behind, or here's the meaning behind if we have a positive value for work or a negative value for work. Since engineering, we're looking at work either entering or leaving a system, just like we will when it comes to heat energy in later chapters. We look at positive work as work that is moving out of a system, and work that is entering a system or being applied onto a system, that is negative work. So, because we got an answer of positive 60 kilojoules, that's work that the air performed onto the surroundings. 4.2, air initially at 300 kilopascals and 500 Kelvin expands under constant temperature from a volume of 0.2 to 0.7 cubic meters. What's the work done by the air? Well, keyword here is constant temperature, so isothermal. We can use our work equation P1V1 times the natural log of V2 over V1. And with that, work will equal 75.2 kilojoules. Positive meaning that that's work that the air is actually performing onto its surroundings. 4.3, air initially at 250 kilopascals at 500 Kelvin expands in an isentropic process from a volume of 0.2 to 0.5 cubic meters. What is the work done? What is the work done by the air? Oh boy. Under this scenario, what's the work performed by the air? Well, isentropic, all that means is we'll use our general polytropic equation, which is work equals the change in the product of pressure and volume over 1 minus n, and n equals gamma in this particular case, 1.4. Now, since for this type of equation, we need to know both the starting and final pressure and volume, we need to use our polytropic equation to solve for what our final pressure is, where P1V1 raised to n equals P2V2 raised to n. Rearranging this, we can solve for our final pressure as P1 multiplied by the ratio of V1 over V2 raised to n. Plugging everything in, we get 250 kilopascals times the quantity of 0.2 over 0.5 cubic meters raised to 1.4, our adiabatic index, and that comes out to a final pressure of 69.3 kilopascals. Plugging this into our general polytropic work equation, P2V2 minus P1V1 over 1 minus n, that gets us a work under an isotropic process coming out to be 38.5 kilojoules of energy. Now looking at 1.4, here's an example of your textbook laying out certain bits of information and us needing to critically think about what is of value. Air with a gamma of 1.4 initially at 500 kilopascals and 400 Kelvin expands in a polytropic process where pressure and volume raised to 1.1 is a constant at the start and at the end of our process, throughout our process. What is the work done by the air as it expands from a volume of 0.4 to 0.7 cubic meters? Well, under this scenario, this is similar to our isentropic process. The isentropic process was just a specific case of this type of general polytropic process. The only difference is when we're solving for P2, our n index is not 1.4. That was only valid under isentropic conditions. It's now some general polytropic condition where the n index is 1.1. Solving for our final pressure, that's 270 kilopascals. So plugging in everything into our work equation and changing the denominator to being 1 minus 1.1, that gives us a work output of 110 kilojoules by the air. 4.5, air is compressed at constant pressure at 400 kilopascals from a volume of 0.7 to 0.2 cubic meters. What's the work done by the air? Well, what we're looking at here is that we have actually a negative change in volume, which is going to cause our isobaric work of P times delta V coming out to negative 200 kilojoules. So a negative value, that just means that where we could say that the work done by the air was negative 200 kilojoules, physically, what that means is 200 kilojoules was applied into the air, was performed on the air itself, entering into the system. 4.6, air initially at 400 kilopascals and 300 Kelvin is compressed at constant temperature. What volume? From a volume of 0.8 to 0.5 cubic meters. What's the work done by the air? Well, constant temperature, work equals P1V1 times natural log of V2 over V1. That gives us work equaling 400 kilopascals by 0.8 cubic meters by the natural log of 0.5 over 0.3 cubic meters, or work equaling negative 150 kilojoules. If we're looking at it from the air doing work, then we would say it's doing negative work, negative 150 kilojoules of energy, energetic work. 4.7, air initially at 240 kilopascals and 300 Kelvin is compressed in an isentropic process from a volume of 0.6 to 0.4 cubic meters. What is the work done by the air? Well, in this scenario, it's another situation where we need both the starting and final pressure and volume. So solving our polytropic equation for P2 and using an n index of gamma 1.4, that gets us 423.4 kilopascals. And I should say that gamma is 1.4 just because we're talking about air it would change if we're talking about some other gas. It could be some other value. Plugging that into our polytropic work equation, that comes out to negative 63.4 kilojoules, the negative sign indicating that work was entering the system during this isentropic process. 4.8, work initially at air initially at 300 kilopascals and 400 Kelvin is compressed in a polytropic process where PV 1.1 is a constant. What is the work done by the air as it is compressed from a volume of 0.5 to 0.2 cubic meters? Well, just like before, we need to know our final pressure, which isn't directly given. So determining it through calculation. Mathematically, that comes out to 822 kilopascals. Since it's not isentropic, we need to use that 1.1 instead of the 1.4. And plugging in our work equation, we get negative 144 kilojoules of work performed by the air, or 144 kilojoules performed on the air itself. 4.9 and 4.10, these are just similar examples about steam, but looking at it from positive or negative work. Let's look at steam expanding at constant pressure at 600 kilopascals from a volume of 0.2 to 0.5 cubic meters. What is the work done by the steam? Well, work is still isobaric in this scenario, so work equals pressure times the change in volume. We have a we have a positive expansion of volume. This indicates that we will have a positive amount of work, which in this case it becomes 180 kilojoules. So during pressure volume work, if a process occurs such that volume expands, that is going to be work that the system is doing on its surroundings. On the opposite, let's say steam is compressed at a constant pressure from 300 kilopascals and a volume of 0.7 to 0.5 cubic meters. What is the work done by the system? Again, it's constant pressure, so work equals pressure times the change in volume. What we have is a shrinkage or a negative change in volume, thus work equals negative 60 kilojoules. While we still can say that the steam performed negative 60 kilojoules of work, more practically what that means is because volume shrunk, the surroundings instead pushed work energy into the steam, adding it to the steam. So work went into the system. Now, those were examples of pressure volume work. Here are some non-examples of pressure volume work. In thermodynamics, we can talk about shaft work, which is work due to some spinning action. And you'll see these in stirrers or fans or turbines. What is needed is a torque and an angular acceleration. With electrical work, that's the work performed by current flowing through electrical circuits. What I should say is we're not looking at work, but work rate. For electrical work rate or electrical power, that's equivalent to current times voltage. And due to Ohm's law, we can replace those values with resistance such that the electrical work rate is equivalent to current squared by resistance or voltage squared divided by resistance. And previously when I mentioned shaft work, really what we're looking at is the the shaft work rate or the shaft power when we take torque times angular acceleration. Not so much work, but its rate. So W dot, that's work rate, that is interchangeable with the term power. Therefore, our units for work rate are watts, kilowatts, or even megawatts. And to go from megawatts to kilowatts, times by 1,000. To go from kilowatts to watts, also times kilowatts by 1,000 to get to watts. So, two examples of each. 4.11, what is the shaft work when a torque of 250 newton meters is needed to rotate a pump shaft of 1,500 revolutions per minute? Well, our torque is 250 newton meters. Those are standard units, but our angular acceleration of 1,500 RPM, it's usually better to have angular acceleration in radians per second. So to solve our work rate equation of torque times angular acceleration, for this example, we're going to need to get rid of RPM and try to convert them into rads per second. So an example of doing that, the shaft power equals 250 newton meters times 1,500 revolutions per minute times 1 minute per 60 seconds times 2 pi radians per 1 revolution. And what that ends up giving us is 39,369 kilowatts, which is a Newton meter per second, Newton meter radian per second. That gives us 39,369 kilowatts. And more often than not, your textbook will take these answers and in megawatts. So if you see your answer in a smaller increment, it's just converted to megawatts. So that becomes 39.3 megawatts of shaft power. Well, that was just introducing the conversion. Let's look at the same equation, but shortening that conversion ratio. What 4.12 was the shaft work when a torque of 300 newton meters is required to rotate a pump shaft of 2,500 RPM? We're still talking about shaft work, so the work rate equals torque times angular acceleration. And just to clean up our conversion factor, let's just take 300 newton meters by 2,500 RPM by 2 pi radians over 60 seconds. Or you could do a pi rad over 30 seconds. That causes the work rate to equal 78,500 kilowatts of power or 78.5 megawatts of power. The last two examples, we're almost done. What we have here is 4.13. That is, what is the rate of electrical power required if a current of 20 amps passes through an electric heater having a resistance of 8 ohms? Well, our work rate equation is current times voltage. And we could use Ohm's law to multiply current times resistance to get voltage, but really let's just simplify everything. The work rate equals IV, or using Ohm's law, equals current times resistance, or I squared R. Therefore, the electrical work rate is 20 amps squared by 8 ohms, or 3,200 watts. Just know in this case, with shaft power, usually our answers come out into kilowatts. When we take torque times acceleration, Newton meters by rads per second, in electrical work rate, what we usually end up with is an answer directly in a watt, not kilowatt, because amps times volts, that is a watt. And lastly, 4.14. What is the rate of electrical power required if a current of 15 amps passes through an electric heater having a resistance of 11 ohms? Similar story, Ohm's law is V equals IR. the work rate of electrical power is IV, or I times IR, I squared R. That lets us have the work rate of electrical power becoming 15 amps squared by 11 ohms, or 2,475 watts, which you could simplify if you wanted to about 2.5 kilowatts of electrical power. So, approaching approaching the 26-minute mark. Thank you all for coming to this engineering thermodynamic lecture on polytropic and non-pressure volume work. We'll be getting into heat later in this semester, but for right now, that is everything for this week. Glad to have you all, and see you next time. Peace.